All right, so K is given to us. Now, let's go ahead and set up our equilibrium expression. We're always, first step is going to set up K. So I'm going to say K set up. So K is equal to what over what? All right, so what's my product here? CH3, CO2, C2H5. Doesn't matter what it is, it's just a bunch of letters. Okay, what else? That's it, because, yes, this is a pure liquid water, okay? Board is really off. But this is pure liquid water, so yes, they give us a concentration, but it's a trick, okay? Do not include it. I'll put an X to that, it's not important. Divided by the reactants, CH3CO2H, and then ethanol, C2H or 5OH. Okay, so what do we know this equals? K, which is what? 4.10. This, I might have to redo this board. This is real bad. 4.10. Okay, and then I need to go ahead and substitute in the values given to me. So I get to substitute in 4.10 is equal to, what was the top number concentration? 0.91. So 0.910 molar. And then that's just a parentheses there. And then we have this one over here being 0.210, and then this one being X. I don't know what that value is. So how do I solve for X? Well, anytime I possibly can, I need to multiply by, if X is in the denominator, I need to go ahead and multiply by X to get it out of the denominator, then the math is easy. So we multiply by X on both sides. That cancels X out over here. 4.1 times X equals to this over this. Well, what's this over this? Actually, you guys can do this. I'm not going to walk you through the steps. Solve for X. I don't think I have to walk you through the math steps, but if you need me, just let me know. What does it look like? Everybody should be calculating because I don't want you to not know how to get to the point where you have to do this for yourself. I know you can do ours though, so just prove it to me. What did you get? How much? Loud and proud? Steady. 1.057 molar. Just as long as it's close like that, that's good. So X, which was equal to the concentration of ethanol, is that. Yay. Okay, easy. You just have to be able to solve for X. I can't deal with this. Quick break. Skilled for now. Okay. Boom. Done. Okay. And one more. Maybe two more. And during experiment, 0.2 moles of hydrogen gas and 0.2 moles of iodine gas were placed in a 1 liter flask. When the reaction was allowed to reach equilibrium, what concentrations of hydrogen, iodine, and hydrogen iodide would occur? Okay, so that information they give us initially, what can that be used to do? Find the molarity. Perfect. So these two values are going to be our original conditions, our original information for these two gases. And then we have the liter. So how do I get to molarity? Moles per liter, right? So I'm going to write an ice box. Okay, this is what I need you guys to write with me because this is going to be the first example of an actual ice box. ICE, where I stands for initial, C stands for change, and E stands for guess. Nah. What kind of problem is this? Equilibrium. Okay. And the question says that it's allowed to reach equilibrium. So we want to get our calculation to equilibrium. That's our goal. We're starting off with 0.200 moles per 1 liter. Well, what's that molarity? What's that molarity? 0.2, right? So you don't have to write it like that. But I'm telling you now, if I give you something that's not 1, you got to make sure you divide first. So if I give you 2 liters, the molarity would be 0.1 molar. Okay, so don't forget to divide by the 2 liters. This one is as well. So I'm going to erase this and actually write in the molarity, 0.200 molar. And the same thing for iodine, 0.200 molar. Because that's what they told us in the problem about the two gases. Did it tell us anything about the hydrogen iodide initially? Before this reaction begins, there is no product. So that we have to assume that's 0 right there for this. And these are columns that I'm making. It's kind of hard to tell, but this is a column representing the H2. This is one for the I2, and this is one for the HI. Okay, so as this reaction occurs, what two things have to react? The two that we know, the two reactants have to react to make products. Well, as they react, what happens to their concentration? Huh? They get used up, so they decay, they decline. So there's going to be an amount that is subtracted from both of these reactants, because that's what I mean when they get used up. The law of conservation of mass means that we can either create or destroy. So we're going to minus some amount. I have no idea what the amount is. So if I don't know what the amount is, I have to call it x. So minus 1x here. Where did I get the 1 from? From that coefficient. It's all stoichiometry. This one, I'm going to minus 1x here from the I2 value. I don't know what this value is, but I can solve for it in the end. But as I create this one, I'm creating it 2 times as fast as I'm consuming the other ones. So how much are we going to add to this side? 2 what? 2x. Okay, so these x's are all proportional, but as I subtract away 1x from here, that's only because these coefficients are 1s. If this was a 3, I would be adding 3x or whatever it may be. Okay, so make sure you look at the coefficients. That's because there's just a proportion here. So at the end of this reaction, at equilibrium, I'm going to have 0.200 minus x. And this one's the same thing, 0.200 minus x. This one's just going to be 0 plus 2x. I'm just going to call that 2x. This information is the most important piece of information that I need now. Because now that I'm done with the icebox, I don't even go back and look at it. I just want to use this bit to plug into an equilibrium value. So we're given the K to be 49.5. I need to go ahead and set up my K expression. Go for it. K is equal to, no, I don't want to, let me go back real fast. The expression, when I say equilibrium expression, I want you to plug in this stuff, the actual reactants and products, not this just yet. So now, tell me what's my equilibrium expression. HI what? Squared, don't forget that 2 becomes an exponent, divided by concentration of H2 times concentration of I2. Okay, now, I didn't want you to go ahead, I didn't want you to plug it in, so I'm always scared people are going to forget the squared, so I always have to make sure we do that first. Alrighty, so I'm going to give myself a little division here. Okay. So K is equal to 49.5, which is equal to 2x squared. I'm plugging in now. I'm plugging in my equilibrium values because that's what we had to get to the E, is to actually be able to plug in equilibrium values. Times, can I just simplify these two things down here? I'm going to simplify them on the bottom. Just square them, right, because they're the same thing. So 0.200 minus x squared is equal to, I'm going to erase K here, and we'll actually put in the K value of 49.5. That looks like some wicked math. How do you guys want to try to solve this? Huh? What's the easiest way to simplify this? Square root, exactly. So if I square root this whole shebang, I get the square root of 49.5, which I don't care what it is yet, I do. That, and then these two squareds go away, so then that's equal to 2x over 0.200 minus x. All right, well that simplified some. How else can we do to solve for x? I can't divide by 2. I can multiply by the bottom, the denominator, but then am I gonna have to use the quadratic? It's gonna be like linear regression, y is equal to mx plus b. This sounds kind of complex, right? I don't want to go that far. So I'm going to show you. Do I want to show you this now? No, sorry. I'm going to show you the next one because there's a method of showing you how to solve for these easier. Someone got that for me? What's the square root of that? 7.035. We are actually, I lied. We are going to multiply by the denominator, which is equal to 2x. So what do we need to do with this number? Distribute, right? So 7.035 times 0.2 is 1.407. And then how does this happen? What happens with this x? Minus 7035, right? X is equal to 2x, and then what do I do? So combine like terms. Add your 7.035 to this side, so then that's 9.035x is equal to 1.407. And then what do? Divide by what? 9.035, right. So divide by this side, because this needs to cancel over here to get x all by itself. So x is equal to, I got 0.1557. Okay, 0.1557 molar. Sorry. All right, I forgot what the question was. Let's go back. We've just solved for x, whatever x is, right? So our question was what are the concentrations of hydrogen, iodine, and hydrogen iodide at equilibrium? Okay, so we got x to be 0.11 or 1557. 1557. Let me write that a little bit better. 1557 molar. That's what x is equal to. X is not the answer though. We have to go back and plug them into our equilibrium values and actually now solve for x through solve for the value through subtraction. So then I'm going to do 2x. Well, what's that times 2? Got you 0.3114. That's this first answer for the hydrogen iodide. These two, I just have to minus that x value we got. So that was the 0.2 minus the x is going to be 0.0443 molar. And that's for this one as well, because they were the same setup. Yeah. I'm going to make sure everything's cool right here real fast. So, yes, these are like half-page problems. My bad. It wasn't me. I'm just teaching you. It wasn't. I didn't make it up. Okay. I'll just go down real fast for anybody who needs that. Let's do one more together, and then I'll let you guys do something. Let me know when you're feeling confident about it, though, because I don't want to, leave you hanging. Okay, now we have a pressure one. Oh, no, kind of. In air, 25 degrees C, 1 atmosphere. I don't really care about any of this right now. Nitrogen is 0.03 molar, 33. Oxygen is 0.00810. Taking the nitrogen and oxygen concentrations as the initial value. So where are they telling you to put it? I in the icebox, right? Calculate the equilibrium concentration of, so the question is, equilibrium concentration of nitrogen monoxide. That's our question. Okay, so we have a value of K as 4.8 times 10 to the negative 31. What does that value tell us? Yeah, it does tell us it's really small. What does it tell us about equilibrium? What about the reactants? All right, so the reactants are favored. What does that mean? At equilibrium, who do I have a higher concentration of, reactants or products? Reactants, right? So high concentration of reactants at equilibrium. All right, keep that in mind as we go through this problem. What do they tell us to do initially? All right, so they say kind of in hidden words, we're going to make an icebox. And, this is like an equal sign. This is 0.033 molar. Oxygen is 0.00810 molar. And nitrogen monoxide is, no, not yet, is 0. Because if they don't tell us we have any initially, we can't assume anything else but, hey, they didn't tell me I have anything, so that means I don't have anything. So you have to call that 0. And as these things react, these reactants are going to decrease. So they decrease by how much? 1x. I don't know how much exactly, so I have to call it x, or related to x. So minus 1x here. And also, since that's also a coefficient of 1, I'm also minus 1x here. But as these react, I'm gaining product, so plus 2x because of the 2 coefficient in front of that product. All right, so then at equilibrium, I have 0.033 minus x. This one's 0.00810 minus x, and this is 2x. All right, this is who I care about right now. What did we do in the last problem? We plugged it into the K expression, right? So let's write out the K expression first before we can plug it in. K is equal to squared over nitrogen times oxygen. Okay, so then I get to plug it in. So K was, what was K? 4.8 times 10 to the negative 31 is equal to, now I get to plug in. So tell me what I'm plugging. 2x squared over what? 033 minus x, right? Times 0.00810 minus x. Okay. Ooh, that looks real complicated. Can I just square root this one? No, because it's not. It's a square root problem. This is the only one that I can square root for sure. These two denominators can't be square rooted because they're not the same thing. So what kind of formula do you think has to be used here? Quadratic. Negative b, plus or minus the square root, plus or minus the square root. I can't remember the quadratic formula. 4ac. 4ac? Yeah. Do you guys want to use it? I don't either. Here is the trick, okay? This has to be done only in one condition. When the reactants are highly favored, we said there's going to be a lot of reactants left and very little products, right? Do you think that x is a really big number or a really small number then? Really small. So small, we can neglect it. Okay, so this x, what I'm subtracting from my reactants is going to be so minuscule compared to what I have of my reactants, I can just ignore it in calculations. But this x, I cannot ignore because otherwise I have to assume it's 0, and I can't put 0 in this because then it's going to give me 0 and k doesn't equal 0, right? So I can't neglect x unless two criteria are met. Really small k. That's the first thing that has to be checked. That has to be true. And that's true here. It's just negative 31. You're cool. What also has to be true is only neglect plus or minus x's. So the x's that are literally like you have in the equilibrium minus x. This one's just 2x point blank by itself. It's not being added to anything because you're adding it to 0, so we call it nothing. So this one's good to keep. These, I'm going to do a little slash through it with an arrow and say assume 0. And this one as well, I'm going to say assume 0. So this is called neglecting x. Yeah. Only neglect plus or minus x's. So then I'm going to go, what I did here, I'm going to do that here as well. Let's assume that's approaching 0, where it's really, really tiny. It's like a limit, I guess you could say. We've done limits. Okay, cool. I'm not speaking foreign languages. So that makes our math like 100 times easier. Then we get 4.8 times 10 to the negative 31 equals 2x squared still, because that's the one we had to keep, divided by, what's the 0.33 times the 0.0081? What is that? Huh? Anybody? 2.673 times 10 to the negative 5th. Thank you. All right, so now how do I solve for x? Huh? This bottom, I just multiplied 0.033 times 0.00810. I took these two numbers that I had left over and I actually finally multiplied them. Because once I ignore x, I pretend x isn't there, and I pretend x isn't there. So then it's just multiplication on the denominator. So when I neglect x, it makes my math like way easy. And that's why I choose to neglect x, because it's a method that helps me get through the problem. And all chemists use it, so I didn't make that up. Okay, so these two things combine together to make this. I need to multiply the denominator and then divide by. You can do square root then, I guess. I was going to say divide by 4, because this up top is not actually 2x squared, it's 2x squared. 2 distributes in to make 4. 2 distributes in to make x squared. Okay, so multiply by the denominator, divide by 4, square root. X equals, tell me what you get. Huh? Tell me what you get, somebody. Anybody? So, okay. That number times this number is 1.283 times 10 to the negative 34 is equal to 4x squared. How do you divide by, or how do you get rid of x by itself? Divide by 4. So that divide by 4, this divide by 4, x squared is equal to, that divide by 4 was I don't know. I didn't solve for that. I'll just put number sign there. And then how do I get x by itself? I have to square root. So x is equal to 5.66 times 10 to the negative 18th. Did anybody else get that when they tried it? Thanks. All right. Were we correct to assume x was itty bitty? Yes. So our assumptions are proved correct because we would have had to figure out quadratic formula, set equal to 0, do all that junk to solve for that. We can easily simplify our math by doing this neglecting x method. Okay, so this is x, and our question was to solve for the concentration of nitrogen monoxide at equilibrium. Well, what is nitrogen monoxide at equilibrium equal to? Look at your chart. To what? Yeah, so this right here is our nitrogen monoxide at equilibrium. It's equal to 2x. So all I gotta do is take my x and do what? Multiply by 2. 2x is equal to concentration of NO, which is equal to 1.13 times 10 to the negative 17th molar. And that also proves our point where we said that reactants are favored. There was going to be a lot of reactants left over and very little products made. That's like almost nothing. So that's definitely true. All right, we got to take a stretch break real fast. You just did hardcore math. All right, stretch break. Do we need to yoga? I mean, I got you.
Hey, yoga.
No, we didn't stand up. Everybody's going to stand up. Get your choice now. Stand up. Some people like sneaking off. That was mainly doing this for your purpose. Get up. Splash some water. Huh? We will. You have to.
Yeah, when are we gonna have our Olympics?
I'm going to do it. You get my
Squad together.
do it.
I can't take that.
We've only been here for like 20 minutes, guys.
At least 25.
25.
Yeah.
Alright, who got that worksheet I gave you yesterday?
Got it right here.
Yeah, I know.
Someone or left back to yell.
I'm discussing that right now. We'll discuss it later. If you need a worksheet from yesterday, come grab one. This is all I have left, so you will have to share. I'm sorry, share your leader station.
That what we're doing?
I'm gonna do Alright, you've got 30 seconds to get back to your seat and stop talking. Move so fast, guys. Alright, Brendan. Thanks. Alright. I'm going to try to get you guys up and moving a little bit. This is kind of hard. It's a Friday. Look at, it says Chemistry, Chapter 18, Worksheet number 1. Is it on there? See, Chemistry, Worksheet number 1. It starts off with hydrochloric acid. Yeah, I think it's on the top right. Somebody at your station needs to share it if you can't see this. Alright, I'm going to go down to number 3. Okay, number 3. We're given 2A. Do not write on this paper either, please. 2A plus 2B. You might want to write out the reaction. Yields C plus 4B. You see this reaction? Yes? Write down the states of matter as well. That's why I'm writing it here, just in case you can't see it. So 2A is a gas. 2B is also gaseous. C is also gaseous. D is a solid. This is number 3 on worksheet number 1. It says write the equilibrium expression. Go for it. I know you can do that real easy. K is equal to concentration C. Dun dun dun.
What is D?
No, these are solid.
We don't do D.
Right. This is a pure solid here, so we ignore it. Okay. Not entirely ignore it, but do ignore it for your equilibrium expression. All right. So that's the first power over what? A squared and B squared. Okay, then it gives us information. The initial concentration of A was 4.0 and B was 4.0. What would be constant, or what would the constant be if at equilibrium 2.0 molar of A has reacted? So we need to make a what here? An ice box. Well, you come on. No, I want to move the whole thing. There we go. Whoa! I'm gonna put you down there. Okay. So I already have my ice box. So I would highly recommend that anytime you write a problem like this out, write your BC at the top and then leave yourself some space for an ice box below, like I've just done here. Okay, so we start off with what of A? 4.0 molar. Thank you. We start off with what of B? 4.0 molar. Okay. What did we end up with A? Or what did it say about A? 2 has what? 2 has reacted. So is that the change or the equilibrium? That would be the change, okay? So we're minusing 2.0 molar here because that's what it said. If I had to write that as x's though, if I didn't know what the change was, what would you have written that in terms of x's? Minus what? 2x, because of the coefficient, right? So right now in my head, I know that 2 molar is equal to 2x. That's how much I would have written. But, so what does that mean x is?
4.
No. X is 1. Thank you. Because if 2 molar is equal to 2x divided by 2, x is equal to 1 molar. So that gives us a big hint on what all these other ones are. So if x is equal to 1 molar, how much would you subtract it here? 2x, so that's equal to 2 molar. And did we have anything initially here? Nah, 0, 0. What about here? What would I have? Well, remember, if you minus from the reactant side, you have to add to the product side, right? So you've added 4. No.
Plus 2.
Look at the coefficients.
Yes.
Okay, I'm gonna write minus 2x down here like I did here, and then you guys just told me the 2b was a minus 2b. That's why I said it's also 2.0. This is a plus x. This one is a plus 4x. Okay, now we know x is equal to 1. So what am I adding here? 1 molar. What am I adding here? 4.0 molar. Right, because it's 4 times 1. Okay, but do I really need the solid? Don't care. Just a big X through it. You don't need that. I'm just trying to show you that sometimes you will actually go through the whole thing. This one is not necessary because it's not in the K expression. All right, so at equilibrium, 4 minus 2 is 2. 4 minus 2 is, guess what? It's also 2. What is this one? 1.0, and don't care. Okay. So then I get to plug it into my K expression. Yes. Because it told me that the change or the reactant A was 2.0. And I know that if I didn't know what it was, I would just have to call them X's, right? I know that I would have had to subtract 2x from there. So then in my head I said, well, the 2x I would have subtracted equals the 2 they told me. So then I solved for x. Okay, so then I need to plug that in. So K is equal to concentration of C, which is what? 1 molar over the concentration of A, which is 2 molar squared, and then concentration of B, 2 molar squared. Can you do that in your head? 1 over 16.0825. No, 0625. 0625. You just did 4. 2 times 2 is 4. Or 2 squared is 4. 2 squared is 4. 4 times 4 is 16. That's not so bad, right? Got this. All right, look at 4. Given A, I'll write this reaction up here as well. Given A plus 2B equilibrates to C plus 3D. What do they say? All gases, so they all matter. Okay. What is the KEQ if initially the concentration of A was, so what am I going to write now? Icebox, right? Leave yourself some space always underneath your BC. The original or initial concentration of A was 3.0 molar. B was 8.0 molar. And at equilibrium, 2.0 molar of C is produced. Where do I put that? Under the E for C, right? So equilibrium is this. And our question here is to solve for KEQ. So I got a lot of box to fill out. But once I know one product, It's all good, baby. We got this. Okay, what do I start with on the C and the D? 0. So how in the world did I get to 2? You added 2, right? Is that equal to x, or is that equal to 2x, or 3x, or what? That's equal to 1x. How do you know? 1's coefficient, right? So if I didn't know this, I would have just said plus 1x. But I know now x is equal to 2.0 because that's what they told me my final was, and there's only one way to get there is to add it. So I'm going to just go ahead and put this here. I'll put the plus x in parentheses so you know that I'm not actually using x's. It's just how we solve for x. So what do I have to add over here in terms of x's on D? I would have had to add 3x, right? Well, what's 3x equal to? 6. So I'm actually adding 6 molar. So down here, this is also 6 molar. Okay? What would have I had to subtract from A? X, and x is equal to 2. So I have to subtract x, which is equal to 2. So 3 minus 2 is 1. And in this one, I would have had to subtract how many x's? 2 x's, which is equal to minusing 4. So a minus 4 is 4. So this gets plugged where? KEQ. I don't even know my expression yet. What's my expression? Concentration of C plus or times? Times concentration of D to the third power over times D squared. Okay, so C is equal to 2.0. D is equal to 6.0 cubed with 6 cubed. No calculator. Yeah. 190. Cool, I love you. Thank you. I don't know that one. And A is 1. B is 4. So 216 divided by 16. 432 divided by 16. What is that? Huh? I mean, if 216 is right, sorry, it's 432 divided by 16. 27 is what I also got in my head. Yes. 27. I like those better. Just the A's and B's. But you're not going to be given all A's and B's because you will have some A's and B's, and then you'll have some like real calculations or real expressions. Yeah.
Why did you subtract up in the for the reactions? Why did you subtract like minus Q and everything?
Because as I no, it's not anything about x really. It's because if I add on the product side, that has to come from someplace, and that has to come from the reactants. Because of the law of conservation of mass. I just can transfer it from one to the other. Okay, are you okay on that worksheet? Let's do another one that's not on the worksheet, and I'll let you guys work by yourself here, or in groups. Yes, we're gonna do ice boxes, but we're gonna revert back to using ice boxes and pH together. Okay, and it's exactly the same thing. It's just now you have one more step and it says solve for pH. All right, so look here, and this one is actually on your lecture notes. Okay, you see on your lecture notes page. So you see down here on the lower left, this lecture examples comes the equilibrium pH of 0.002 molar nitrous acid. It's got a Ka value next to it. If you don't have that worksheet, I'll get you one too, but I just want to let you know that that's there. Let's do number 1 first. Ready? So I have 0.22. I need this. Here's my example. And I'm not giving a whole lot of information. First, so we've gone through, we see that first thing we normally write is a BCE and K expression. KQ expression. So let's first write our BC for this. We have nitrous acid, and it says Ka. Remember that Ka means acid dissociation constant. What does it mean to dissociate? To what? To move away, to break apart. So like, I didn't like Brendan, I would like to dissociate from him and just not associate with him. I would not be his friend anymore. Okay? So disassociate means to break apart. That's all it means. Okay? I have nitrous acid. What's that formula? HNO2 And acids usually react with water to form what? Nope. Well, kind of they're ions. Aqueous, Arrhenius aqueous, right? That's aqueous water, liquid water. How does an acid act in aqueous solution? Creates hydronium, H3O plus. How did that happen? This H did what? It donated itself to water, leaving leaving what behind? NO what? NO2 what? 1 minus, thank you, because it's lost the charge as well. Alright, so we're going back to our acid-base stuff. Alright, so here's my reaction finally. Now I have information that starts me off. It says, what is the pH of a 0.002 molar solution? Where do you think I'm going to put that number? Look, it says this solution of nitrous acid. Well, who's nitrous acid up here? HNO2, right? So I have to put it underneath that one. And this is initial. So we have an icebox here. So initially, I have 0.0020 molar of that. I'll put some of the other O. Alright, and this is a strong or weak acid? Weak, because it's not one of the 6, right? Nitric acid, HNO3, is the weak one. You can also confirm that it's weak because look at that number, 4.5 times 10 to the negative 4th. That's so weak. It's so small, right? It's not even large. Being 1 is large here. This is weak. All right. So this right here does not 100% dissociate. That's why we have this reversible arrow, because some of it's going to dissociate, some of it's going to go back. How much is that sum? I don't know. I'm going to call it X. Some of this will disappear. I'm going to subtract some of that. And I call it 1x because of the fact there's a 1 coefficient. Then, did it say I started off with any of these products? No, so I assume 0 and 0. How much get added to the product side? 1x and 1x, okay? So then I have at equilibrium 0.0020 minus x, x, and x. Alright, so far I've set up my BC. I got my ice table taken care of. What have I not done yet, though? I have not written my what? KEQ. So KEQ is equal to whatever what? Can't make your head up. What is it? H3O times NO2, 1 minus, over HNO2. And why not? You see, you notice I just ignored water here, right? I don't even put a number there. Just put a big, huge slash through that. Scratch it out. You do not need it. You need it for the reaction when you write your BC, but you do not need it in anything else. Okay, so then I have hydronium and then nitrite. They both represent, but they're represented by the same thing, which is X, correct? Those X's can go plug into the numerator, X times X. And then this number, the minus X goes in the bottom, 0.0020 minus X. If you can't see, there's some couple spaces up front where there's lab stations. That looks like it's going to be quadratic. I'm feeling it. So if I simplify this a little bit more, I notice that KEQ, which was, what was KEQ again? 4.5 times 10 to the negative 4th. 4.5 times 10 to the negative 4th is equal to, simplify this to be x squared, yes, in the numerator, over 0.0020 minus x. Ooh, I don't like that. What would you guys want to try? But then I gotta like, set equal to x squared, and then it's the quadratic formula. So, what did we try earlier and our assumptions were correct? We're assuming that it's 0. We neglect x. It's called neglect x. So, which x's can I neglect? Only the minus one, right? So, here I'm going to put slash 0. Here, slash 0. Oh, so much easier. 4.5 times 10 to the negative 4th times this number, 0.02, gives me something. And then I just have to get the square root and I get x. Yes. Reactants? Well, let me show you right here. This really small, that weak acid, got a really small K, so it can do that. So it is possible. And I'm looking for my answers. What did you guys get when you got X? 9.5 times 10 to the negative 4. Good job. So when you multiply these two numbers here, you got 9.0 times 10 to the negative 7th is equal to x squared. And then you had the square root. And x equals 9.5 times 10 to the negative 4th. Okay, but we haven't even answered the question, guys. What was x? What did I solve for x? Okay, our goal is to find the pH. Well, which of these babies is going to actually tell us the pH? The HNO2 I cannot plug into my pH formula. Hydronium, H3O+. What is the pH formula? I've forgotten.
Oh.
pH equals negative log of H3O+, right? This is the most simple formula we can get. Guess what? Our X is equal to H3O+. Look right here. This X is this H3O+. So I'm going to scroll back up here. If X is equal to hydronium, then we just get to plug X into the pH formula. So here we go. pH equals negative log of hydronium, 9.5 times 10 to the negative 4th. It's probably like 3.2. Anybody? 3 point what? 02. Yay! pH and equilibrium in the same question. You don't want to do labs. These are the hardest labs that we do in AP. Yeah, just stop. Okay, so I'm going to stop for now. I'll pick back up later. Those of you who, I'll pull up the questions for you in the lecture notes. There are 1 through 5. At the top, we have not done yet. I'm going to see where I am. It starts with phosphorus pentachloride, deals with phosphorus trichloride and chlorine. Work through some of this right now for the next 20-ish minutes, and we'll jump back in and do a couple things. Read on the back of the lecture notes. We'll put this up here. Do work.